So let's look at this question here. So it's here, name and draw and name the organic product of this following reaction. Right? So number 2 states that, okay, so I have a benzene here. I'm going to draw it out this way. And then what I'm going to do is I'm going to react it with CH3Cl, so methyl chloride, and then and then my catalyst here is aluminum trichloride, right? Aluminum trichloride. What am I going to get? And I get some product plus HCl, right? Plus HCl. So I'm again, another classic predict the problem in this case. So again, take a moment to think about this problem here. What would this do in terms of when I'm reacting with a aromatic compound? I have benzene, which is very, 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 very stable. But then again, I have this AlCl3, right? So what does that do to the benzene? Does it do anything here? So again, think about this problem, and we'll look at it together. So take a minute to go think about this problem here. So again, you can think of this as the aromatic compound is very electron rich, right? It has a negative charge here. So I'm looking for a positively charged thing here, right? Positively charged thing here. So, okay, so again, just a little hint about this. So again, what we have here is benzene, and we have CHCl3, right? So again, I'm just a methyl chloride in this case. And then what we want is we want product, right? So this is a classic example of a Friedel-Crafts alkylation. So let me write this down. This is a Friedel-Crafts alkylation. And how do we know it's a Friedel-Crafts? Well, first I have a Friedel-Crafts. Well, the first giveaway is that I have a benzene. If I have benzene, it doesn't really react. Benzene here is pretty unreactive just because it's very, very stable, right? I have here, it's again a resonance stabilized compound. I have delocalized electrons, and what does it mean is that these electrons, these double bonds are, you can think of them as jumping around, but it's aromatic compound. So these double bonds are constantly in motion, and they're very stable by itself. So this is a Friedel-Crafts alkylation, and we know that because there's a benzene, and this is a dead giveaway. The reagent, the aluminum trichloride here, and and then this here is what it's going to be. This reagent here is part of the Friedel-Crafts, and it's going to activate the alkyl halide. So what does that mean? What does that mean when it activates the alkyl halide? So what it does is, I'm going to draw the mechanism here. It's going to I have here, again, CH3 is the positive charge, and this is the negative charge here. Aluminum has a positive charge. Actually, let me color coordinate this. Sorry. So this blue is a positive charge, and Cl is negative here. Aluminum is positively charged, and the chlorine is negative. Sorry. Negative, right? So what it's going to do, this CH3 is going to get activated by the aluminum trichloride. So what it does is it's going to do some black. It's going to bond with this aluminum. So it's going to make, let me redraw my arrow here. It's going to make, actually let me just erase this because I'm going to draw the mechanism here. So it's going to activate this methyl group. And what it does, it's going to make something like this. It's going to make some type of this is Cl here. It's going to bond with the AlCl3 here. And what it does is, in this case, this would have now a positively charged chlorine, and then this would have a negatively charged So this is activated now. This is a big electrophile, right? Because I have here this carbon CH3 here has a oh, sorry, I didn't color coordinate this. Give me a second. This is a positive charge here, and then this would be just the carbon here, and then this is the H3, this is the methyl group, right? And if this here is the positively charged positively charged chlorine here, again, this carbon here is also this here is also positively charged, right? It has a dipole partial positive, right? So what it does is it wants to kick this out, right? It's going to this aluminum is going to, it's a really good leaving group than chlorine. So what it means is it's going to, this is now being activated, right? So this chlorine is simply just going to leave, and then I create something called a carbocation. So what that is, it's simply just a or sorry, this entire thing is going to leave, because this here, you can think of it as ALCL4, right? ALCL4, this entire thing is going to just get kicked out here. So this entire compound is going to get kicked out. That's what makes it a good leaving group, which means I get H3C plus here. And this here is very, very, very unstable. And because this here is a carbocation, right? This here, it wants something that's negative, right? Carbocation. It wants something that's very, very negative. And the last, where's my negatively charged to satisfy this positive charge? I have a resonance stabilized here, electron rich, right? So I have here a carbocation. It's going to then attack one of these bonds here, and then it's going to make my Friedelscraft product here. So I'm going to draw that. So I made the carbocation, and basically what that does is it's going to, if I add this with my benzene here, and I guess again, the benzene here is electron rich, right? This here is, this here is a positively charged, so it's in blue. A positively charged carbocation. This here is, you can think of it as a negatively charged, because it's electron rich, right? It's negatively charged, so it's going to attack this, and then it's going to make, finally, my product, which is benzene, and it's just a methyl group here. So this is a Friedelscraft classic example of a Friedelscraft alkylation, right? I'm adding an alkyl group to my benzene, right? So classic Friedelscraft's alkylation here. Sweet. So let's look at the product here, and again, it's correct, right? Again, my product here, I put it on this carbon. It doesn't matter. I could rotate this benzene. It still would make this compound here. So again, I don't like how they don't use the mechanisms here, so I'm just saying good solution. However, missing step by step, because it's just to fill in the blank, right? Missing step by step mechanism of alkylation of Friedels, and this is a Friedelscraft, right? So I'm going to state Friedelscraft's alkylation. So the solution is correct.